Okay, everyone. Hello. Welcome back to the afternoon session. So it's my great pleasure to introduce our next speaker, Fabrizio Grandoni. Fabrizio has this uncanny knack of finding long-standing barriers and breaking them. And so it's our great pleasure to have you here, Fabrizio, to talk about some more of your exciting work. So whenever you're ready, the floor is all yours.
Thank you very much. And thanks to all the organizers for inviting me to this nice workshop. Thanks a lot. So a little advertisement at the beginning. So I'm the local organizer of Soda 23, which this year is in Florence. So most of you know, Soda is one of the main conferences in PTAS. And usually it is in the United States. Rarely it is organized abroad. And so I think it's a great chance to have such an important, beautiful conference in Europe. And I hope that the European community, including Britain, Switzerland, Israel, can support these events by coming, because there will be clearly less people from the United States for different reasons, cost, time, visa issues, and so on. And so it's important that we compensate that with a lot of enthusiasm and participation. So if you can come, even without a paper, please try to come. If you have money to support your PhD students, postdoc to come to Florence, please consider that. And let me also mention that this event, this Soda in Florence, is also in large part due to the work of Arthur behind to make this possible. So now let me talk about my talk. So I'm going to talk about unsplittable flow on a path. So this is a problem I've been working on for a very long time, 10 years, about 10 years. And then I will mention also some related problems, open questions. And so this is the definition of the problem. So essentially you're given a graph, which is a path. Each edge has a capacity, UE, positive capacity. And then you're given a collection of n tasks. And for each task I, you have a subpath, a demand, and a profit, or weight. So a feasible solution is what? It's a subset. Then I will show you an example and it will be easier to follow. But anyway, so a feasible solution is a subset of tasks such that for each edge, the total demand of the tasks in your solution that use that edge, meaning that the path contains that edge, is at most the capacity of the edge. So it's a very natural constraint, working constraint. So for example, if you have a single edge, this is the knapsack problem. If your path contains only one edge. And then your goal is to maximize the profit, a natural task. This problem has a natural interpretation where essentially your graph is a time interval subdivided into time slots. And at each time, in each time slot, you have a given amount of some resource, for example, energy. Think about energy. And then your tasks are jobs that you can execute or not. If you execute them, you get some profit, but then you have to satisfy the constraint. For example, the total energy required by the task that you execute at a given time cannot be more than the available energy at that time. And so there are applications in different settings based on this model, like caching, bandwidth allocation, and so on. Now, this name, this is a really terrible name that we didn't manage to change for this problem, because what's unsplittable on a path? There is nothing splittable here, right? So there is an historical reason that there is this famous problem, unsplittable flow on a graph, where essentially you have sourcing pairs, and if you want to route some demand di from source Si to Ti, you also have to specify a path. In the splittable version, you have to specify a single path. But in the graph case, you might also split your flow through different paths. So there is a splittable version of the problem. And in that case, it makes sense to talk about splittable or unsplittable. If you project this problem on a path, then the routing part becomes trivial, there is nothing to split, and then you get this unsplittable flow on a path. So if you want to remember this problem, think about the general graph case, and then you project it to the path case. So an example, so we have this path graph. Each edge has a capacity that is represented by these horizontal segments, and they induce some capacity curve that we will use at some point. Then for each task, we interpret each task I as a rectangle whose height with some profit. So the height of the rectangle is the demand of the task. And then the width corresponds to the number of edges in its path. Okay, and then you have a bunch of these guys, and then, for example, you can take the red rectangle, the green one, the blue one. They all fit together in a feasible solution, but you cannot take the yellow one because, for example, on this edge, you will exceed the capacity. So is the problem clear? Because otherwise, the rest is not understandable. So I think it should be simple enough. Okay. So the problem is clear. So let me remark that this is not a geometric packing of rectangles. There is a variant of the problem where you do that. So in particular, you know, this blue rectangle is split in two parts because you just care about the total demand on each edge, okay? For example, for energy consumption, this makes sense. In other settings, it doesn't make sense. So this is the case. So there are a few reasons why I do like UFP, this problem. So it's simple to state, very natural problem from a mathematical point of view. It has natural applications. It also has several variants and generalizations. I will mention some of them. So if you don't work on the main problem, you can work also on the side problems, challenging open problems, and also historically, the study of UFP led to many new algorithmic and analytical techniques. So this is a rich source of new ideas that can hopefully be applied to other problems. So this is a good mix for a problem to be interesting, I think. Now I go a little bit more into technical details. And I need one definition which is helpful to understand the main results in the area that I will later illustrate. So for each task I, you can identify the minimum capacity of any edge along its path. So for example, for this task I, the red edge is one edge with minimum capacity for this task, okay? That's called the bottleneck edge and the corresponding bottleneck capacity of the task. And now, given this definition, we say that a task is delta large for some constant delta if its demand is at least delta times its bottleneck capacity. So on some edge, the task consumes a delta fraction of the available capacity, available capacity. Is this clear? So for example, this task is 1/2 large because on this edge, its demand is at least 1/2 of the capacity of the edge. But on some other edge, the demand of the task can be much smaller than the capacity. Okay? So if this happens on a single edge, then the task is delta large. Otherwise, it is delta small. And this gives you a partition. For a fixed delta, you partition the task in two sets. This is used in the approximation algorithms. That's why I'm insisting a little bit on that. And now some results. So the problem is strongly NP-hard. And so it makes sense to design approximation algorithms for it. And in the early 2000s, there were a few results on the uniform case, which is when all the edge capacities are equal. Okay, in general, on each edge you have a different capacity. Imagine they all have the same value. This problem is already non-trivial, and there was a 2 plus epsilon approximation at some point. And how do you get that? you have an algorithm for small task and one for large task. The best of the two gives you a 2 plus epsilon approximation. So this was the main approach for many years, also for the general case. Now, if all the tasks are small, there is a PTAS. So what is a PTAS is, for any constant epsilon larger than 0, is a 1 plus epsilon approximation running in polynomial time. And this result is based on LP rounding. I will tell you roughly how it works. It's not too difficult. Then Bansal et al. Got a Q-PTAS for the general case with some restriction. So the Q-PTAS is defined similarly to a PTAS, but the running time is not polynomial, it's quasi-polynomial, which means n to the polylog n. And most people believe that when you have a Q-PTAS, then also a PTAS exists. So this was a strong indication that the right target was to get a PTAS for this problem. And this was not excluded by strongly NP-hardness. Okay? Then there were Lagrange approximation, first non-trivial one in polynomial time, but the first constant approximation was achieved by Bonsman et al. And here they made a very surprising, in my opinion, connection with another famous problem, which is maximum independent set of rectangles. So I will explain you the connection in the slides. So in this talk, I'm not only talking about my own work, I'm also illustrating a little bit of the previous work. And then with Anastopoulos and other authors, we managed to get a PTAS for large tasks as well, only, getting a 2 plus epsilon for the general case. Then there was this Q-PTAS without restriction by Batra et al., where they introduced the slack lemma, which was also used in future work. So in this area, I must say that many of the previous ideas were needed to reach the next result. So they were incorporated in the subsequent work somehow. It was a very collective and constructive way to achieve the final result. And then, so in this work with Momke et al., we got a PTAS for the rooted case, which is the case where all the paths use some edge. There is an edge that is shared by all the paths of the tasks. This might seem a trivial problem, but even this single problem is non-trivial. And so the main idea in this work that was also useful in subsequent work is a kind of reduction to the resource augmentation case. So in the resource augmentation case, your solution is allowed to be slightly infeasible, so you can violate edge capacities by a 1 plus epsilon factor. And in general, but you compare with the optimum solution, which cannot do that. And in general, this type of relaxations can change can substantially simplify the problem, even change its complexity status. For example, you can turn an NPR problem into a polynomial time solvable one by this relaxation. But our intuition was that this is not the case for UFP. For UFP, actually, the resource augmentation case is as hard as the general case. But the reduction is useful because then the algorithms get simpler, because you have this little slack that you can use for example, when you round things and so on. And then, again, with Monk et al., we managed to break the two approximation barrier, one of the barrier mentioned before, and here you need to put together small and large tasks. This was not a substantial amount of them, clearly. This was not easy because the approaches used in the two cases were very different. For large tasks, we were using dynamic programming. All the works were using some sort of dynamic programming. And for small tasks, LP rounding, so somehow you had to combine these two things that are not very easy to combine. So this was difficult. And then in the previous soda, we improved a little bit the approximation factor. But here the interesting thing is the technique, in my opinion, not the factor. So we introduced the notion of a solitary game formulation of the algorithms, and I will speak about that. And I think this idea can be helpful. Maybe it's the take-home of this talk. Can be helpful for other problems as a technique. And indeed, it turned out to be the right approach for this problem because later on we obtained a PTAS. Finally, we got a PTAS for UFP using the same type of approach. A different type of game, but the same approach. And so maybe the same technique can be also applied to other packing problems. Okay, so do you have questions so far?
I have a question.
Yeah.
If I'm not mistaken, like the complementary version where we want to minimize the cost of intervals that you did not schedule is 4 approximation with this?
I don't remember the approximation. It's like UFP covering, it's called, right? It's an interesting problem. At the very beginning, I was thinking about the problem, but then I went to the UFP and I forgot the details, so I don't know. I don't remember exactly which is the status for that problem. So you understood the question, no? You can ask the question, I mean, you want a mean cost subset of tasks such that you reach the capacity, at least meet the capacity of each edge. In that case, you need to provide some service, cover something in some sense. It's the covering version of the problem. That's also a nice problem. Okay, other questions? I have to check the time. So if not, I will now tell you something more about some results in the literature. I don't have time to describe many of them, all of them at least, but I will mention a few. So first of all, I can tell you something about small tasks, where LP rounding works. So in particular, Cheguri et al. Proved the following result, that for any constant epsilon, larger than 0, there exists a delta larger than 0 small enough, such that you can get a 1 plus epsilon approximation if all the tasks are delta small. Okay, so this delta will depend on epsilon. And this result is not difficult. It uses a very nice, clever technique, which is called randomized rounding with alteration. And I will illustrate it for the simpler case where you have uniform capacities equal to U. Okay? But the basic idea is similar. It's not, in general, it's not difficult, not too much difficult. So first of all, so you solve the standard LP for the problem, which is this one. So you have variables xi, which are 1 if you take the task, 0 otherwise, in the integral version. And then the constraint is that on each edge you cannot exceed the capacity of the edge for the selected tasks. So this is the simplest LP you can think about, this problem. And then you want to minimize the cost of the selected tasks. So is the LP clear? This is a very simple one. This is called the standard LP for UFP. Now you do the following. You solve this LP, and now you consider the tasks in increasing order of the leftmost edge of the task in its path. Let's call it Li. And you do the following. If the current task I fits together with the previously selected tasks with the same process, then you select it with some probability. So the probability, as you can imagine, is given by xi, the LP value, but scaled down by a little amount, 1 minus epsilon. Okay, so this is the alteration in the name of the technique. And now the idea is the following. Which is the expected demand of the task that you previously selected and that use edge Li, the leftmost edge. So by the order in which we process tasks, all the previously selected tasks start to the left of the current one, right? So the most critical edge is the leftmost one of I. If things go well there, then you have no problems. You can add the task. So there is a single critical edge. And since the expectation is 1 minus epsilon u, if your tasks are delta small for a delta small enough, but still constant, then using Chernoff bound, the probability that you cannot insert the current task is small, is only epsilon. So you can actually You can add it with probability 1 minus epsilon, and then you will add it with some probability, which is 1 minus epsilon xi. So essentially, you almost recover the LP value, which also shows that this LP has a very small integrality gap for small tasks. Okay, so this is a nice technique. Maybe you can keep it in mind as a LP rounding technique. Now, this doesn't work for if you also have large tasks, as you can imagine, otherwise we would be done already immediately, right? And indeed, the standard LP is very bad in that case. So this is an example where that shows that. So imagine that all tasks have a unit profit, and in this case, you can take only one task in an integral solution. So opt is 1. However, if you set all the variables to 1/2, you can essentially you get a feasible LP solution of value n over 2. So the integrality gap is omega of n for this problem. So the standard LP is really bad in general. Sorry, for non-uniform capacities at least. Okay, now I told you what you can do with small tasks, and let me tell you something about large tasks. So first of all, let's start with a simple case that the capacities are uniform. Now, in this case, for any constant delta, we can even compute the optimum solution. The problem is not NPR. And the reason is essentially is a simple exercise on dynamic programming that you can also give to your students probably. So how do you solve this problem? So I will be quick. So for each edge E, you can consider all the possible ways you can have a feasible subset of tasks using that edge. Since the tasks are delta large, you can have at most 1 over delta of them. So you have a polynomial number of options. And then the DP table, corresponding DP table entry is the profit that you can get from tasks that start, let's say, to the right of this edge. They are fully contained to the right of this edge. Something like that. No, I mean, I will not give you all the details, but this is a simple DP that works for large tasks and uniform capacities. And this already essentially explains you how you get a 2 plus epsilon approximation for uniform capacities, because you can just take this algorithm for large tasks, the LP rounding algorithm for small ones. The best of the two solutions is a 2 plus epsilon approximation. Is this clear? At least the basic idea? So small, large, 2 different algorithms, the best of the two is good enough. Okay? So this is for the uniform capacity case. What happens if you consider large tasks and you do not have uniform capacities? Here, the situation is substantially more complicated, and actually it took several years of work to get something for the general case. This is an example that shows that, so in this example, essentially, all the tasks can be included in a feasible solution. And you see that on the rightmost edge, you have all the tasks. And these tasks are delta 1/2 large, actually. Sorry. These tasks are 1/2 large. Okay, so despite the fact that they are 1/2 large, you can have n of them on a single edge. So you cannot use a efficient dynamic program to solve this problem, because you have too many tasks on a single edge to remember, right? Okay, so there were a few works trying to do something for this case. As I mentioned, we got even a PTAS for that at some point, a complicated one. But let me mention one of those results that I think is very cute, and which led to the first constant approximation. So this is the result by Bunzman et al. They proved that if the tasks are 1 over k large, then you have a 2k approximation, which means that it's a constant approximation, in this case a constant. And this implies a constant approximation for UFP by the same argument that I mentioned before, right? You use one algorithm for large tasks, one for small, you choose the delta somehow, some compromise, and then you get a constant. And this result is based on a connection with another famous problem, which is maximum independent set of rectangles, another problem that I really like a lot. So here you are given a collection of axis parallel rectangles in the plane, and you want to find a maximum weight subset such that no two rectangles in your solution overlap. For example, for this instance, the red and yellow rectangles form a feasible solution. So is this problem clear? It's a very famous problem. Now what this problem has to do with UFP. This is the surprising part. So Bosma et al. Consider the following process. You imagine the task as rectangles, as I said a few times already, that initially are below the path. Then you lift them up until they touch the top part of the capacity profile, like this. Okay, you just do this. They will touch it at some point and you stop. So now each rectangle is inside the capacity curve. And so first observation, by the way, this induces an independent set of rectangles instance, no, on the plane in particular. And so first observation is that if you give me an independent set of rectangles, that's a feasible UFP solution. For example, if you take these three tasks together, they form an independent set of rectangles, and it's also a feasible UFP solution, right? Because it's impossible that you exceed the capacity of any edge with an independent set, right? Is this okay, intuitively clear? So this is the easy part, right? An independent set is a feasible solution. The converse is not true. For example, if you look at the green and blue tasks, together they can be in a UFP solution, but certainly they are not in a feasible independent set of rectangles, right? So it's not true that that every feasible UFP solution induces an independent set of rectangles. That's false. And the surprising fact that they proved is that computing an independent set of rectangles is not a too bad solution. It's a 2K approximation. In particular, you can 2K color every feasible solution such that each color class induces an independent set of rectangles. So this is a very cute result. So this doesn't solve the problem yet, because when this paper was written, there was no constant approximation for independent set of rectangles. So you were transforming a hard problem in an even harder problem to approximate somehow. It was not a great transformation. But the instances of independent set of rectangles that you get from this construction are easier, are special and easier. Indeed, you can even solve the problem exactly in polynomial time via dynamic programming. So this was enough for them to get a constant. And now, okay, I still have time. I try to be, not to put too many slides, so I don't need to rush. And I will spend a few words about the PTAS for UFP that we finally got. So this is a very complicated work, technically complicated. It's about 60 pages, and also uses a lot of previous stuff. So altogether, I don't know, maybe it's twice the number of pages to know everything. But I will tell you only some simple ideas that I think can be helpful, and also you might be able to use them in other works. In particular, I want to speak about this technique that we use, which we call randomized sketching, which is maybe not a great name, I don't know. So the basic idea is that we model UFP algorithms in the form of a certain type of solitary games. And So you can choose the game, essentially, and you have to design a good game for the problem to have a good approximation. So the basic idea is that you have a player, and you present tasks to the players one by one, according to some order. The order also can be critical, somehow. And then, essentially, the player has to decide to take the task if it wants to take, or she wants to take the task or not. Select the task or discard it. And this is an irrevocable decision. So you will see a task only once, and if you discard it forever, and vice versa. Okay? But now there is something more interesting happens, is that after the player selects a task, if the task is selected and it is small, then we flip a coin and we change the demand, artificially change the demand of the task. We set it to 0 with some probability and otherwise to some large value. So you can imagine that either you set the capacity to 0 or you transform your small task into a large one somehow. So this is the idea. Clearly you want to keep the expectation of the demand. Why do we do that? So the idea is that thanks to the rounding, the number of possible scenarios that the player can see becomes polynomially bounded, and therefore you can compute the best strategy for the player in polynomial time. So which is the best strategy? The one that maximizes the expected profit, because this is a random process. So the profit is as some random variable, the maximum profit that you can get. So then, hopefully with the example that I will give, this will be clearer. And there is a final complication. The player might compute infeasible solutions. For example, it might happen that the player is very lucky, many tasks are rounded down, and then you can put many more tasks, she can put many more tasks than it is actually possible. So you also need some rounding procedure at the end to transform the outcome of the player into a feasible solution without losing too much. So this is the kind of the basic idea. Now, in the following, I will do the following. I will focus on uniform capacities again for simplicity. And I will give you an example of a game that does not work. So that's not the game that we used. But at least you see the basic idea. You can get a flavor of what we do, what happens. Okay, so now let's see the game. So first of all, the order on the tasks is very, very simple. We process them in increasing order of leftmost edge, like in the, I don't know, for example, in randomized rounding with alteration. So we start with the blue task, then the red task, the violet one, and so on. So this is the order in which tasks are presented to the player. So when some tasks are large, some are small, so the rules are a little bit different in the two cases. So let's start with large task. For a large task, the player can select it or not. For example, it decides to take the blue task. So far nothing happens. Now, what happens when the player selects a small task, like the red one? So in this case, so the task is selected, and now we flip a coin. With some probability, we set the demand of this task to 0, and with the complementary probability, we set it to delta U. So remember that delta is the threshold for between large and small tasks. So we transform, in that case, a small task into a large one artificially. Okay, so we are changing the demands. In this case, the player is lucky, the task is rounded down to 0, so essentially in the following steps, we can forget about it. It consumes 0 demand. And then maybe, I don't know, the violet one doesn't fit, then maybe it selects the orange one, which is again small. We flip the coin, this time it is rounded up. So the probabilities are set such that the expected demand of each task is the same as in the input. Okay, the rounded demand is a random variable. Its expectation is the original demand. So we continue this way, and this is some game, right? Did you get the basic idea? So the game that we use is something like this, more complicated. The rounding is a little bit different, but the idea is similar somehow. For example, you can see that for this game, computing the best strategy of the player is not too difficult. You can use a kind of dynamic program where you incorporate the expectations, right? Like probability that a task is rounded up or down. So this is for you students, is the next exercise on dynamic programming with expectations. A little bit more complicated, okay, for the good students. Now, to show that your game gives you a PTAS, you need, or it's sufficient to have three main lemmas. One is efficiency, that you can compute the optimal strategy of the player in polynomial time. For example, for the previous game, that's not hard to get. And in general, this is not the hard part of the proof. That's typically not too difficult. Second lemma is that there exists a strategy of the player which has a expected profit close to the optimum profit. This is typically harder to prove, but not too hard. And then there is the nasty part of the argument, which is roundability. So essentially here what you want is that given a strategy of the player, what is a strategy? It's each possible decision of the player in each possible setting of the game. And then you want to compute a feasible solution whose profit is an expectation close to the profit of the expected profit of the player. So if you have these three things, then you get a PTAS. For the game that I described, profitability doesn't really work, but almost. Roundability fails miserably. So you can build strange strategies of the player where, for example, the player gets profit only when too many tasks are rounded down, and therefore you get highly infeasible solutions only, and you can build very bad cases for that. And so this type of approach doesn't work for that game, at least. But we managed to find a more complicated game that works. Okay, so this is the basic idea. So maybe remember this idea of transforming the demands of small objects into larger ones randomly, which in plugging problems allow you to use dynamic programming, essentially, type of approaches. And then you hope that some sort of Chernoff bound helps you to show that things cannot go too bad. Okay? But it's not, I mean, in some problems it's not so easy. For example, for UFP, it took a very long time for us to understand the right strategy. Now, I should conclude. Maybe shall I mention a couple of open problems, or shall I stop here? What do you?
Yeah, you can go ahead.
Okay, so quickly. Storage allocation is the geometric version of this problem where you really want to pack rectangles. For example, in this case, the blue rectangle cannot be added to the solution. In UFP, you might add it, but here you cannot because the red and blue together, they don't fit as rectangles. And so this makes sense, for example, if you need a contiguous amount of a given resource. For example, you need contiguous memory locations. Then you really need to pack these rectangles. This is a nice problem that might admit a PTAS. We have a 2 plus epsilon approximation. I guess this can be very hard, technically hard to achieve, but it's a nice problem, nice open problem. Then back UFP. So in this case, tasks are partitioned into subsets, and you are allowed to take at most one task per subset. They are called bags sometimes. For example, imagine that each color defines a bag. So in this case, you cannot add the right red task even if it fits in terms of capacity because you took already another one. So this is a special case of a submodular version of the problem, to mention another case where submodularity is interesting. And I like this problem. It is apex hard, so no PTAS for it. So it's harder than UFP, strictly harder. And the best approximation is only logarithmic. So maybe, I mean, getting a constant is a nice problem. This is one of my favorite problems in the area now. And there is also a special case of it, which is nice, where essentially for each task, you have also a time window, and you can shift horizontally the task inside the time window, right? So this is also, so this has some scheduling flavor. So you have a release time, deadline, and you can decide where to schedule this task. You can model this with a bag where you essentially for each, you make a copy of the task for each possible position where you can schedule it. And this is polynomial reduction, so it's really a special case. And again, a constant is missing, and we don't know if the problem is apex hard, though I think we have a proof now of this fact, so don't work too hard on that. And you can ask the same question on a tree, unsplittable flow on a tree, where the best approximation is log square n, which is terrible. Maybe log n is possible, maybe a constant is possible. So here, the problem gets much more complicated on a tree. And, well, let me stop here. Thank you.
Slightly over time, so perhaps while John sets up, a quick question for Fabrizio. Okay, so feel free to catch him at the coffee break. I'm sure he'll be happy to answer your questions, so thank you.
Thank you.